Assalamualaikum warahmatullahi wabarakatuh. And hello everyone. My name is Abdul Akmal because Nizam, trick number 147172. We are from group 3, and in this video, we are going to look on analysis of COVID-19 transmission dynamic in Malaysia with SIRS model. Before we continue, this is our group member. For now, let's talk about introduction. COVID-19 is a major health threat across the globe which causes several acute respiratory syndrome (SARS), and it is highly contagious with a significant mortality. In this study, we conduct a scenario analysis for COVID-19 in Malaysia using a simple universality class of the SIR system and extension thereof. That is the inclusion of temporary immunity to the reinfection problems and limited medical resources scenarios lead to the SIRS types model. As a case study, the COVID-19 transmission dynamics are investigated using daily confirmed case in Malaysia, where some of the epidemiological parameters of this system are estimated based on the fitting for the model to real COVID-19 data released by the Ministry of Health Malaysia (MOH). Thus, for this project, we would like to observe the dynamical behavior of SIRS model from a journal article, which is number 3, and compare its data to the current one. Now, let's talk about objective for this project. First and foremost, by employing an epidemiological system of interest, examine the transmission dynamic of COVID-19 and the dynamical behaviors of the model. Second one, to determine the steady state of the system, especially with appropriate conditions. And the last one is the reproduction number, R, that indicates how contagious an infection disease is. Thank you.
Good day, I'm Jack Chai, and I will be talking about the first part of the methodology. This is the model, which are made up of 4 ordinary differential equations, where n represents the total number of populations, st represents the susceptible population, it represents the infected population denoted by the variable, rt represents the removal class, eta represents the birth rate, v represents the death rate, delta represents the transmission rate, phi represents the recovery rate of population, epsilon represents the reinfection force, rho represents the medical supply per unit time, phi represents the half saturation constant. Also, to investigate the impacts of the limited medical resources on the spread of COVID-19 outbreak, the term rho I divided by phi plus I is employed. In the absence of the reinfection force and the shortage of medical resources assumptions, that is epsilon equal to rho equal to 0, then the system is represented by a simple SIR model. All of the parameters are assumed to be non-negative to depict the biologically meaningful phenomena of COVID-19 transmission dynamics. This model becomes a SIRS type system with a rate of transfer from R to S, that is epsilon, is added to this SIR model. The reinfection force, epsilon, can play an influential role in determining the transmission dynamics of COVID-19. Now, we will move on to obtaining the steady state of the model. The steady sets can be calculated by setting all the time derivatives in the model equal to 0. We let ds over dt equal to di over dt equal to dr over dt equal to 0. Then we will obtain equations 1, 2, and 3. After that, they are rearranged to get equations 4, 5, and 6. The resulting system will be solved simultaneously to obtain the steady states. First, we combine equation 4 and 5, and it becomes equation 7. Then, we substitute equation 6 into equation 7 to obtain equation 8. After that, we will simplify equation 8. When I equal to r equal to 0, we have A is equal to eta multiplied by n divided by v as our disease-free equilibrium. And it is the desired step that would be M in planning any control measures. From epidemiological viewpoints, this disease-free steady state depicts the eradication of the disease and prevent the spread of the infection. Also, we can obtain the pandemic equilibrium with some S star, I star, and R star that satisfy the equation. This steady state demonstrates the persistence of the disease and the COVID-19 infection can spread in the community with some cases generated daily.
Hi, I'm Han Zhou, and I will continue with the methodology part. In the last session, we already introduced about the SIR model and we find the steady states. To study COVID-19 pandemic in Malaysia and understand the long-term outcomes of the disease outbreak, we need to analyze the qualitative behaviors of the model. This can be done by employing local stability analysis. Thus, we can evaluate the stability of steady states that we have obtained by using Jacobian matrix J, which is as shown in the slides. By using the Jacobian matrix and local stability analysis, the dynamical behavior of the model and the nature of steady states can be assessed to understand the qualitative outcomes of this epidemiological system. The stability of a particular steady state can be deduced from the eigenvalues. This crucial information is obtained by solving for the characteristic equation of the matrix. For instance, we found that there are 3 eigenvalues for the disease-free equilibrium. And note that all the epidemiological parameters are positive. Thus, lambda 1 and lambda 2 are less than 0. If lambda 3 is greater than 0, then the 3 eigenvalues for disease-free equilibrium have different sign, and thus this steady state is unstable and pandemic steady state can be stable. On the other hand, if lambda 3 is less than 0, then the 3 eigenvalues for disease-free equilibrium have the same sign, and thus this steady state is stable and pandemic steady state can be unstable. Next, I'm going to introduce the basic reproduction number, which is R0. This is one of the ways to quantify the severity of transmission of disease. This quantity is an epidemiologic metric used to describe the contagiousness of disease. It is defined as the number of secondary cases one case would produce in a completely susceptible population. Basically, we can divide the basic reproduction number into 3 conditions, which is when R0 is less than 1, R0 is equal to 1, and R0 is greater than 1. When R0 is less than 1, that means the disease will disappear and the pandemic will eradicate eventually. When R0 is equal to 1, then the disease will not disappear, but at the same time, the pandemic will not occur. And last but not least, When R0 is greater than 1, that means the disease will spread rapidly and the pandemic will occur. To obtain the basic reproduction number R0, first, we need to assume that the limited medical resources is relaxed, which is rho equals to 0. Next, we perform an eigenvalues analysis to the SIRS model. That is, by setting some lambda I equals to 0, we can get the following equation. After that, we rearrange this equation to obtain the basic reproduction number. When the numerator part is greater than the denominator part, this will give us R0 is greater than 1, and thus the pandemic will occur. Conversely, R0 will be less than 1. Then we can say that the pandemic will eradicate.
Hi, I am Ong Ying Quan from Group 3 and I am going to present the results and discussions part. First of all, our method is use the SPP to draw the time series graph and our code is shown as follow. First part of our code is the equation and we use ABCDE to assign the variable eta, delta, epsilon and so on from the equation before. And then the parameter we use is from the research paper where the epsilon value is very low. Then our initial condition also from the research paper with this value, and we add these three initial condition together, we will get the n value. Yeah, and this is our code lah. And one thing to mention, right, is the bound here. This bound must be greater than our n value here, because if not, the SPP will not cannot draw the graph. Yeah, and this is our graph from SPP. We use the parameter we talked before here, and the back color line is the susceptible, and orange line is the infection, and the red line is the recovery. So we take a look at the infection curve here, and you can see the case will increase and it will decrease after a period to literally no case, and will increase again at about 3,000 days, which is around 8 to 9 years already. Yeah. Okay, next we can calculate our reproduction number from our parameter, because the parameter we use is we obtain all the parameter already, right? And we can calculate the R0, and this is our R0, and we observe that it is greater than 1. So from R0 we can observe that the pandemic will occur, which is very obvious, since from the graph also we will see the infection case will increase at the beginning. Yeah. Next we consider our steady state. This steady state is a disease-free equilibrium where this steady state will determine whether our pandemic will gone or not lah. And we can calculate the eigenvalue from the formula before, and this is our eigenvalue. Not that all the sign is equal, so our this eigenvalue is a stable knot. Okay, next the pandemic equilibrium SIR, we can find it from our SPP, and this is the steady state. And from this for this steady state we can calculate the eigenvalues shown as follow. And first of all, this is our steady state, and the Jacobian matrix is this, and we can find the lambda value, and this is our lambda value. And not that this is positive and this is negative, so this pandemic equilibrium we can say is unstable saddle. Yeah. Okay, finally we can compare our result with our time series graph. From our result for the eigenvalues, we can see that the disease-free equilibrium is stable and the pandemic equilibrium is not stable. So we can say that we will approach to more to the disease-free equilibrium and away from the pandemic equilibrium, where we can observe from our time series graph here that the pandemic will slowly decrease over time.
Hello there, I am Mohamad Faiz bin Fadzlul Rahman, metric number 147904, and I will be continuing on with section 3, results and discussion. And in this section, I will continue on with solving the steady state with Mathematica. So here's the following. Using Mathematica, we will have to have that when we input the following parameters as previously mentioned, n equal to 0.006, or technically is the n with the long leg on the right, and also the m is actually the uppercase n for different reasons when we're using Mathematica. However, when we input the following values 0.0006, 0.002, and so on, and we create the following equation, which is a system of differential equations, and we apply the solve function with equation 1 equates to 0, equation 2 equates to 0, equation 3 equals to 0. We want to solve for s, I, and r. We obtain that s the following value 555,792.5, I 0, R 0. That's the first steady state. The second steady state is S equals to 55,240.3, I equals to 5.76017, R equals to 546.421. Continue on, we have the last steady state, which is S equals to 44,666.8, I equals to 143.2, and R equals to 10,982.5. So that's how we solve the steady state of a system of linear equation, a system of differential equation, using Mathematica. We input the values and we use the solve function there. Continue on. I will also talk about the conclusion of our project. That is, say, what is our government efforts in combating COVID-19 outbreaks? So, for the Ministry of Health Malaysia, or H, play an important role to contain the spread of the virus, which is one, an enforcement of health screening at all points of entry. Number 2, increase the number of hospitals that could treat COVID-19 cases, as lack of number of hospitals cause digestion to its hospital staff, and also implementing the movement order control to limit the spread of the virus between state lines. That is one of the government efforts in combating the COVID-19 outbreak. So, in this project, the main lessons learned from this model is that we learn a lot about the importance of the eigenvalues in the epidemiological system, or for the eigenvalue analysis. We also learn about the reproduction number R that indicates how contagious an infectious disease is. As we see from the previous in section 3, we calculate the reproduction number, we obtain that it is greater than 1, so it gives us a criteria for an outbreak. And fourth, that is all from us. And here are the references that we have used from. Number one, the Bernama coronavirus have ministered without screening and entry points. Number two, the Edge Markets Malaysia bans public events to curb COVID-19 spread. And number three, the Bernama Health DG Movement Control can boost in the ministry's fight against COVID-19. And that is all from us. Thank you very much for listening to our presentation here. From all our members, we thank you very much. That is all.